corrections from yesterday that actually folks in the class pointed out. So first of all,
Okay. All right. So Xiaolong is going to talk to us about light echoes, sort of continuing on the theme of kind of unsupervised learning, anomaly detection, and so on. He's a postdoc at Space Telescope, working with Armin Rest. So yeah.
Okay, thanks, Michael.
Yeah.
Okay, so thanks, Michael, for the invitations. I'm a postdoc in Hopkins. I work on some AI stuff and light echoes, and also working on preparing for the Rubin LSST. So today I want to show you guys how we can apply the AI object detection algorithms to sky survey images so that we can automate the detection of objects in for future sky surveys. So the cases we use here is as the light echoes a bit. So a little bit about the background, science background about light echoes. So when the transient and first, imagine that transient like a supernova and the Earth are at the three-dimensional ellipsoid, and the light from the ellipsoid from the supernova that reflected on anything such as the interstellar dust will arrive the Earth at the same time. So when there's uniform dust distributed around the supernova, what we can observe is perfect circles that surrounding the initial transients, such as the supernova 1987A, the top images. And if there are only part of the ellipsoid has the dust, we can only observe part of the ellipsoid, such as the below images. And because as time goes by, the light travels, and the three-dimensional ellipsoid looks like it's like expanding, and we observe the circles looks like expanding outward to the initial transient. So that echo is because the echoes arrives the Earth at later times, so it provides us a unique opportunity to study transient. So such as the Tycho supernova. By study we didn't observe the Tycho supernova using modern telescopes, but by light echoes give us a chance to study using modern telescopes, study the spectral Tycho supernova light echoes of Tycho supernova. We can, and comparing the spectra of the light echoes by the Tycho supernova template, we can verify that Tycho supernova is a type 1A. And also light echoes we can construct the light curves of transient from the echoes, such as this is the images from echoes of Eta Carina, and Eta Carina has great eruptions in 19th century, last about 20 years, but we didn't observe we didn't have the observed by modern telescopes. We only have some visual estimations, historical record of the changes of the brightness. The top one is the estimations of brightness change recorded by people in 19th century. And the below light curves is the light curves we can reconstructed from these echoes by monitor the changes of the flux in fixed positions. Yeah. And the echo, because the dust is a three-dimensional structure, by observe the echoes from. Sorry. Okay, by observe the echoes in three dimensions, we can study the asymmetry of the transient explosion. And also the time evolution of echoes provide us invaluable information about the dust surrounding the transient, which is otherwise invisible. Okay, so how we detect light echoes? Echoes are usually very faint, and echoes is not a point-like sources, and it's time evolving, it's moving, and is usually missed by modern telescopes. And this can be automated by computer vision algorithms, such as the object detection frameworks, such as region-based ones, and other algorithms can tell us which part of the images there's an object, and so the AI algorithms can be pretty useful for modern surveys, such as the LSST. By then we will got a lot of images. It will be feasible to visual inspection by humans. So how can AI help in detection light echoes? So the most straightforward way is to using a convolutional neural network by using the convolutional neural network to do the feature extraction, and tells us whether there is echoes in the images or not. The other approach is that the neural network can not only tell us whether there is echoes in the image, but also locate the exact positions in the images. This framework is pretty useful for large images, large field of view, such as ZTF or LST. Okay, so the other approaches, like the segmentation approach, this can tell us about not just the locations, but also the boundaries. Each pixels is belongs to the echoes in the images. So in today's exercises, we are going to try two of them approach. One is a simple neural network. We will use a popular model called the VGG16. This has about 16 convolutional layers, and after the convolutional layers, you do a binary classification to detect whether there's images and whether there is stars. We label the echoes as 0 and stars as 1. And neural networks are usually treated as a black box, but we can do some experiment to figure out, to kind of understand a little bit about how the model make predictions. One exercise we can do is by plot the Cilius map. Cilius map is Cilius map highlight which part of the images is most relevant to the predictions. This is usually done by take the gradient of the output scores to the input images and map the gradient to the images. So it shows us how the importance of each pixels. And the other exercise we can do is try make some feature maps. So the feature maps, this can be done by we input random images and take gradients relevant to the one of specific layers. And optimize the input images to maximize one of the layers in the neural networks, and the optimized images will tell us what kind of patterns in the input images can maximize the output layers responses. So, and this exercise, we can generate many fancy feature images. The steps is by select the layers and using the PyTorch as a forward hook function, which can get the output from a specific layers and take gradients of this layers relevant to the input images and use the gradient descent to optimize the input images. And after a few steps, we can get the feature maps corresponding to these specific layers. And we can like input the images of stars and to take a look at which features get higher responses, and take a image of star echoes and have a look at which features which activation layers got the higher values, and comparing the difference in feature space for the input images. So in the feature space, like we can using some kind of unsupervised learning techniques such as the TS. When you this plot, this is a dimension reduction algorithms which plot the such as the VGG 16 and output more than 500 features, 500 dimensional feature space. We can use the dimensional reduction algorithms to give us insight about where the echoes located and where the star located. So similar input such as the stars is expected to located in the same nearby regions, and if there are any outliers in the input, it will appear somewhere outside. Okay, so and there's another notebook. We will try a region-based neural network called faster RCNN, which can tell us about not only whether there is a image echoes in the image, but also where and locate the exact bounding boxes around the echoes. So the fast RCNN contains mainly three parts. The first part is a feature extraction neural network part. And the second part, the one is the region proposal. It makes some regions of interest to locate object that is interest in the images. And the final third part make a classification and bounding box regression. And it's classify what object is inside the bounding boxes, and also it's regression to a bounding box regression to locate the exact creations. So the first thing will have four losses. So the losses from the region box proposal. It contains the loss of object to whether there is an object in the bounding boxes, and also the bounding box regression loss, which is the difference between the labeled bounding boxes and the predicted bounding boxes. And also the third part have also two losses, loss for classifier and the loss for the bounding box regress. So when training the fast RCN, we add all those four losses and do a back propagations. Yes, for the last part, we do some evaluations to make to see how the model performance. So the evaluation for the region-based models can be done by can use some criteria such as the IOU intersection over unions. It measures the difference between the predicted bounding box and labeled bounding boxes. So yeah. Yeah, I think that's all I have to say, and the notebook is in here. I hope you enjoy the notebooks, and let me know if any questions.